You've just been handed the ultimate cheat code for the universe. Instant communication, no delay. Think about that for a second. You whisper a secret here, and your friend on the other side of the galaxy knows it right now. Not in 100,000 years. Now. That's what quantum entanglement promises, right? That's the sci-fi dream. Two particles linked magically across space, able to send messages faster than light. It's a story so compelling, so seductive, it's plastered across every headline, and it is completely, utterly, devastatingly wrong. This isn't a story about breaking the universe's speed limit. It's a story about something far stranger, a secret hidden in plain sight, a secret that Richard Feynman saw with terrifying clarity. What if I told you that when you measure one entangled particle, you aren't sending anything to its partner? No signal, no information, not even a whisper. You're not communicating at all. You're just discovering a truth that was written the moment the universe began. Stay with me, because by the end of this, you'll understand why entanglement is so much weirder and so much more profound than mere telepathy. Now, before we dive into this rabbit hole, and trust me, it's a deep one if you're the kind of person who gets annoyed when pop science glosses over the truth to sell you magic, hit that subscribe button. Because on Think Beyond Physics, we do the exact opposite. We channel Feynman's spirit. We strip away the comforting lies and show you the cold, hard, beautiful reality underneath. And what we're about to uncover is a reality so counterintuitive it will make your head spin in the best possible way. Subscribe, and let's get this illusion sorted out. So let's set up this illusion properly, because it feels like communication. It looks like it, smells like it. Imagine we take two electrons and entangle them. We arrange it so they have a linked property. Let's say they're spin, which is just a quantum version of a tiny magnet pointing up or down. The rule of this entanglement is simple but bizarre. If one is found to be spinning up, the other must be spinning down. It's a perfect correlation. We don't know which is which until we look. They're in a fuzzy, shared state of possibility. Now, we put these two electrons in boxes. I take one box with me on a rocket to a planet 10 light-years away. You stay here with the other box. The moment I arrive, I open my box. I peek. My electron is spinning up. Instantly, I know, with absolute certainty, that yours, 10 light-years away, is spinning down. That knowledge traveled from my planet to yours in 0 time, faster than light. It seems like my act of looking here caused yours to be down over there. I sent you a cosmic bit of information. I'm up, you're down. That's the story. And it seems logical. It seems like the only explanation. Why else would you know my result the instant I learn it? Here's what nobody tells you right away. The first crack in this beautiful illusion. Ask yourself a simple question. What can you do with that instantaneous knowledge? Can you send a message? Can you transmit the word hello or a picture of a cat? Let's try. Before I leave Earth, we agree if I want to send you a 1, I'll make my particle read up. If I want to send a 0, I'll make it read down. Seems straightforward, but there's the catch, the one that breaks everything. I can't make my particle be up or down. When I open the box, the result is random, a perfect 50-strike coin toss. I have no control over it. So I open my box and I get up. Great! I just sent a 1, right? But wait, I just sent a 1, right? You, back on Earth, you open your box. You see down. What does that mean? Does down mean 1 or does it mean 0? You have no idea. Because from your perspective, you just got a random result. You can't tell if my result was up or down. You only know your own. To know I sent a 1, you'd need to compare notes. You'd need to call me up on a radio and say, hey, I got down, what did you get? And that radio signal? It's limited to the speed of light. The spooky action at a distance gives you a random string of data, not a message. It's like we each have 1/2 of a random coin toss, pre-recorded at the beginning of time. I look at mine, you look at yours, and we discover we have matching opposites. But I can't change my half to encode a thought. This is where the real mystery begins. If it's not communication, what the hell is it? Before I reveal what's really happening, and trust me, Feynman's explanation will make you question the very nature of reality itself. You need to understand one crucial bedrock principle that Einstein himself held sacred. A principle that entanglement seems to shatter into a million pieces. You need to understand what physicists mean by locality. The idea that for something here to influence something there, a signal, A force, something has to travel through the space in between. No skipping, no jumps. This principle feels like common sense. It's the foundation of all classical physics, and quantum entanglement at first blinding glance looks like it's setting that principle on fire and dancing on the ashes. But what if it isn't? What if the problem isn't with the particles, but with our deepest assumptions about what reality is made of in the first place? Let me show you what I mean. To unravel this, we have to go back to the birth of this weirdness, and to the man who fought it tooth and nail, Albert Einstein. The year is 1935. Quantum mechanics is young, brash, and infuriatingly successful. It makes predictions that work with insane precision. But to Einstein, it felt wrong. It felt incomplete. It talked about probabilities and fuzziness, not certainties. It said, particles don't have definite properties until you measure them. To Einstein, that was like saying the moon isn't there when you're not looking. He believed in a realist universe, a universe that exists independently, with things having real, definite properties, whether we observe them or not. God does not play dice with the universe, he famously growled. So together with his colleagues Boris Podolsky and Nathan Rosen, Einstein set out to expose the absurdity of this new quantum theory. They didn't just write a critique. They crafted a devastating thought experiment. We now call it the EPR paradox, after their initials. Their argument was brilliantly simple and logical. It went like this. Take our two entangled particles and separate them by a great distance. Now, according to quantum mechanics, neither particle has a definite spin until it's measured. It's in a superposition of both up and down. But, Einstein said, consider what happens when I measure my particle here. I instantly know the spin of your particle over there. I have gained certainty about a physical property of an object that is far away. Since no signal can travel faster than light to tell that distant particle what to be, the only logical conclusion, Einstein argued, is that the distant particle must have already had that definite spin all along. It was a pre-existing fact, a hidden variable that the fuzzy quantum description was just too clumsy to account for. The correlation wasn't spooky. It was just two gloves being sent to opposite sides of the earth. If I open my box and find a left-handed glove, I instantly know you have a right-handed one. No magic. The handedness was predetermined when the gloves were packed. Einstein's point was devastating. Either quantum mechanics is incomplete, because it doesn't describe these hidden facts, or it allows for spooky action at a distance, an instantaneous, faster-than-light influence that violates relativity. He was sure no sane physicist would choose spookiness. He'd trapped the quantum weirdos in a logical box. For nearly 30 years, that's where things stood. A philosophical stalemate. The EPR paper was a ghost in the machine of physics. Most physicists, led by Niels Bohr, shrugged. They offered a counter-argument that was, frankly, even weirder. Bohr essentially said, you're asking a meaningless question. It's not that the particle doesn't have a property until you measure it. It's that the concept of it having that property independently of the measurement setup is not a part of reality. The property isn't just unknown, it's undefined. It's not a glove in a box. It's something else entirely. But this was metaphysics. Poetry. There was no experiment to decide who was right. It was a matter of taste. Do you prefer Einstein's comforting clockwork reality with hidden gears? Or Bohr's fuzzy participatory universe where measurement creates reality? This was the landscape when a young, irreverent physicist named John Stuart Bell arrived on the scene. Bell wasn't part of the old guard. He worked on particle physics by day, but he was fascinated by the foundations. And he looked at the EPR argument and saw something everyone else had missed. He wondered, could we test this? Is there a way to experimentally distinguish between Einstein's hidden variables and Bohr's spooky quantum weirdness? In 1964, in a paper of breathtaking clarity, Bell derived what we now call Bell's theorem. And this is where it gets wild. Bell imagined a way to probe deeper than just up or down. Instead of measuring the particle's spin along just one axis, like just checking for left or right-handedness, what if you could check them at different angles? Tilt your detector a bit. Ask a slightly different question. Einstein's hidden glove theory, where everything is predetermined, makes very specific predictions about how often the particles will agree when you ask these tilted questions. It's a statistical prediction. Quantum mechanics with its fuzzy superpositions makes a different statistical prediction. The math is complex, but the outcome is simple. The two theories give different testable numbers. Bell had found a crack in the stalemate. He had translated a philosophical debate into an experimental recipe. If experiments matched Einstein's hidden variable predictions, reality was local and real. If they matched quantum mechanics predictions, then either locality, no faster-than-light influence, or realism, things had definite properties, had to be abandoned. One of Einstein's sacred cows had to be sacrificed. Think about the sheer audacity of this for a second. A theorist with pen and paper had laid out a path that could decide the fundamental nature of reality, but for years it was just a theoretical curiosity. The experiment seemed impossibly hard. You would need to create entangled particles, separate them, make ultra-fast random measurements at different angles, and compare results with insane precision to see which statistical pattern emerged. It was a dream, but then in the 1970s and early 1980s, technology caught up. Physicists like Alain Aspect in France built the machinery. They performed the experiment. They closed the loopholes. They asked the tilted questions, and the universe answered. The results did not match Einstein's hidden gloves. They matched the bizarre, spooky predictions of quantum mechanics with staggering accuracy. The Bell inequality was violated. Reality, it seemed, had chosen. Either information was zipping faster than light, or the very idea that particles have independent, definite properties was a comforting fairy tale we tell ourselves. This was huge. It wasn't a matter of taste anymore. It was data. Cold, hard, reproducible data that said our classical intuition about how the world works is fundamentally provably wrong at a deep level. But that's not even the strangest part. Because this is where most pop science stops. They say Aspect proves spooky action, faster-than-light communication, but they miss the entire second half of the story, the part that Feynman understood, the part that answers our original question. Because Bell and Aspect didn't prove communication was happening, they proved our classical picture of reality was broken, they set the stage for the real explanation. And to get there, we have to leave history behind and step into the quantum world itself. All right, we're at the heart of it now. We have this experimental fact. Measure one entangled particle and you know its partner's state instantly, no matter the distance. But you can't use it to send a message. Einstein's hidden variables are ruled out. So what's left? Let's build this understanding piece by piece, and I promise, by the end, the why will click in a way that changes everything. First, let's dismantle the communication idea from another angle. Imagine the entangled particles aren't gloves. Let's use a better analogy, one that Feynman loved, correlated coins, but not normal coins, magic quantum coins. We create a special pair. The rule is when they are finally flipped and observed, they will always land on opposite sides. One heads, one tails. We don't know which is which until we look. Now I take my coin to Mars. We agreed at exactly noon. We both flip our coins. I flip mine. It comes up heads. Instantly I know yours is tails. But did my flip cause yours to be tails? From your perspective on Earth, you just flipped a coin. You applied a force with your thumb, it spun in the air, and it landed on tails. Your entire experience, the feel of the coin, the spin, the clatter on the table was local and complete. You didn't feel a jolt from Mars. Your coin's outcome wasn't forced by my measurement. It was just the outcome. The correlation is global, but the experiences are completely local. This is clue number one. Whatever is happening, it isn't a traditional cause and effect signal traveling from A to B. Now here's where your brain might start to protest. You want to say, okay, but the information that they're opposite still traveled faster than light. The fact that I know yours is tails traveled from Mars to Earth instantly. But hold on, did a fact travel or was a fact revealed? Think of it this way. Suppose before we part ways, I write heads on a piece of paper and seal it in an envelope. I write tails on another and seal it. I randomly give you one envelope and keep the other. I fly to Mars. At noon, I open my envelope. I see heads. Instantly, I know your envelope contains tails. Did my opening my envelope here on Mars change the piece of paper inside your envelope on Earth? Of course not. The content was fixed the moment I gave it to you. All I did was discover a pre-existing fact about a distant object. This is the hidden variable, or glove model, that Einstein wanted. But we already know this model is wrong because of Bell's theorem. The quantum coins are not like these pre-written envelopes, so the analogy breaks down. But its breakdown is the key. Quantum entanglement is weirder than sealed envelopes. It's like we have a single unified probability object that straddles the distance between us. Not two separate coins with a hidden plan, but one mathematical entity describing the pair. When I measure my part of this entity in a specific location, the entire entity, the description of the whole pair, collapses instantaneously into a specific state. There's no travel time, because there's no distance in the space where this probability object lives. It's not in space-time in the way a baseball is. It's a wave function, a set of potentialities. My measurement here doesn't send a signal through space to affect your particle. It updates the global description of the system. Your particle's state is just the other part of that updated description. But wait, you might say that still sounds like spooky action. Updating something over there because of something I did here. And you're right, it is spooky. But here is Feynman's crucial insight, the one that cuts through the noise. This update cannot be used to transmit information. Let me show you why with absolute ironclad logic. It all comes down to what you, the person with the other particle, actually experience. From your point of view, sitting with your particle, what happens? Nothing unusual. You have a particle in a box. You choose to measure its spin along some axis you pick. You press a button. Your detector clicks. It gives you an answer, up or down. That's it, a single, random result. It looks and feels exactly like measuring any ordinary, unentangled particle. There is no stamp on the data saying, this result was influenced by a measurement 10 light-years away. There's no jolt, no flag, no anything to distinguish it. The raw data stream from your detector is just a string of random bits. Heads, tails, heads, 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 tails. Completely random. For you to detect a correlation, for you to see the spookiness, you need something else. You need the other data stream. You need to get on a classical radio, slower than light, and ask me, hey, what sequence of results did you get? Only when we compare our two lists, side by side, do we see the miracle. Every time I got heads, you got tails, and vice versa. The magic isn't in the individual results. It's in the correlation between the two lists. And that correlation can only be established by exchanging information the old-fashioned slow way. The entanglement creates a correlation that is only apparent from a God's-eye view, a view that requires classical communication to assemble. Now here's where it gets even weirder. Let's introduce a choice. What if we don't both measure the same property? Remember Bell's tilted questions? I measure my particle's spin along the vertical axis, but you measure yours at a 45-degree angle. In this case, the results are not perfectly opposite. They agree some of the time and disagree some of the time in a very specific statistical pattern predicted by quantum mechanics, and not by hidden variables. But again, from your solo perspective, you still just get a random string of bits. You have no idea what angle I chose to measure at. Your data looks random whether I measured vertically, horizontally, or not at all. The choice I make over here does not change the local randomness you experience over there. It only changes the statistical relationship between our two datasets after we compare them. Since you can't see that relationship without my data, sent at light speed or slower, you cannot tell what choice I made. Therefore, I cannot use my choice of measurement to send you a signal. This is the no communication theorem in action. It's a mathematical proof that the operations you can perform on one half of an entangled pair cannot alter the probability distribution of possible outcomes for the person measuring the other half. In plain English, nothing you do to your particle can make my particle do anything statistically different than it would have done anyway. I will always see 50-50 randomness. You cannot encode a message into my randomness. It's impossible. So let's synthesize what is actually happening. We have a pair of particles described by a single, non-local wave function, a shared state of existence. When I interact with my part, the entire wave function updates. This update is instantaneous and non-local, but it is also sub-empirical. It doesn't change what any single observer sees in their own lab. Each observer sees only local randomness. The weirdness, the spookiness, is a property of the correlations between different observers' records, correlations that were baked into the wave function from the moment of entanglement. Those correlations are only revealed through classical communication. This is why Feynman would say entanglement isn't communication. Communication implies the controlled transmission of information. It requires a sender who can encode a message and a receiver who can decode it from the signal they receive. Entanglement provides none of that. It provides a shared random secret established in the past, whose contents are only discovered later through local actions and compared via slow classical mean. It's like two people receiving halves of a torn lottery ticket at the moment of creation. They travel apart. One person scratches off their half and sees the number 7. They instantly know the other half also has the number 7. But they didn't send the number 7. The number was always there from the tear. And the person with the other half still has to scratch theirs off to see it. No information traveled at the scratch. A pre-existing correlation was simply revealed. But we're not done yet, because this still leaves a massive, gaping philosophical wound. If there's no signal and no hidden variables, then what does it mean to say the particles were correlated in the first place, if the properties aren't real until measured and the measurements are space-like separated, meaning no light signal could connect them? Then in what sense can we even talk about a shared reality? This is where we step from the mechanics into the metaphysics, and where Feynman's true lesson lies. This is the hardest part to swallow, the part that separates a pop science understanding from a real one. We have to let go of a picture, the picture of two separate, independent particles. That picture is a lie our brains, evolved for a classical world, are desperate to hold on to. Feynman didn't bother trying to make it comfortable. He pointed at the math and said in his typical way, "This is how the world behaves." If you have a problem with that, well, that's your problem. The math says the entangled pair is a single, irreducible system, period. Think of it not as two coins, but as one abstract object that has two faces we can access in different places. I'm here, you're there, and we can each poke our face of the object. When I poke mine, I get a random result. When you poke yours, you get a random result. But the rules of the object dictate that our random results are intertwined in a very specific way. The randomness isn't independent. It's shared. It's correlated randomness. The object itself isn't located in the space between us. It's simply described as having aspects here and aspects there. This is what non-local truly means. It doesn't mean something is moving super fast between locations. It means the physical description of the system refuses to be chopped up into separate local pieces. Now, let's get concrete with a number because Feynman loved concrete numbers. Let's say we do the aspect experiment. Our detectors are 10 meters apart. The measurements are timed so that they occur within 10 nanoseconds of each other. A light signal would take about 33 nanoseconds to travel 10 meters. So, from the perspective of a photon, my measurement event and your measurement event are space-like separated. There's no time for a light-speed signal to connect them, even in principle. In the relativistic sense, there is no absolute before and after. Some observers moving at high speed would see my measurement happen first. Others would see yours happen first. There is no universal consensus on the order of events. This is critical. If there were a hidden signal, it would have to be faster than light, and it would have to pick a favorite frame of reference to define the order of sending and receiving. But relativity says no such favorite frame exists. Quantum mechanics, in its glorious weirdness, is relativistic at its core. Here it doesn't need one. The wave function update is instantaneous in all frames. It's not a process in space-time. It's an update to the mathematical object that describes the system, an object that lives, in a sense, outside of our conventional space-time picture. The correlation is a primitive brute fact of the universe. Here's another way to see it, a thought experiment that kills the communication idea dead. Imagine we entangle not 2 but 3 particles in a special state called a GHZ state. It's set up so that if we all measure our particles in a certain way, the product of our 3 results, multiplying them together as +1 or 1, is always predictable. Now, we separate to 3 corners of a triangle. We each choose, at random, the instant before measuring, which of 2 properties to measure on our particle. We press the button. We get a result, +1 or -, individually, pure randomness. Afterwards, we come together, slowly, and compare notes. We only look at the experiments where we all chose to measure a specific matching set of properties. And when we multiply our 3 results together, we find it's always, say, +1. Not just often. Always. This is a 3-particle correlation that is stronger than any classical predetermined scheme could ever produce. It's a signature of genuine quantum entanglement. Now, could any one of us have used our choice of measurement to send a signal to the others? Impossible. From any individual's perspective during the experiment, the other two people made random choices and their own result was random. The stunning correlation only emerges in the global analysis after the fact. No one had any inkling of it during their local measurements. There was nothing to detect, no signal to receive. This is the essence of the quantum world. Reality is not a collection of localized, definite things. It is a web of correlations and potentials. Entanglement is the thread of that web. When we say the particles are entangled, we are saying there is a statistical relationship between possible future events measurements that haven't happened yet. The wave function collapse isn't a physical wave traveling. It's the updating of our knowledge of that web of potentialities when one part of it becomes an actuality. And because the web was not local to begin with, that update appears instantaneous. But let's be brutally honest. This still feels deeply unsatisfying. It feels like we're describing the universe as a pre-recorded movie where we're just discovering our lines. And in a very limited, specific sense, that's not entirely wrong. Some interpretations of quantum mechanics, like the block universe view compatible with relativity, lean into this. In that view, all of space-time, past, present, future, exists as a static four-dimensional block. Entanglement correlations are just geometric facts within that block, written into its structure from the beginning. My measurement here and now, and your correlated measurement there and then, are just two events connected by a universal consistency rule. There's no dynamical influence because, in the block, everything just is. My conscious moment of seeing up and your conscious moment of seeing down are equally real fixed points. The correlation was always there. Other interpretations, like the many worlds interpretation, take a different but equally mind-bending route. They say there is no collapse. When I measure my particle, the universe splits. In one branch, I see up, and you, in your branch, see down. In another branch, I see down, and you see up. Both branches are equally real. The correlation is enforced because the splitting happens in a coordinated way for the entangled system. From inside a branch, it looks like I got a random result and you got the opposite, but from outside, all possibilities are realized. Again, no faster than light signal, just the unfolding of a multi-branched reality where everything that can happen does. Feynman was famously pragmatic about these interpretations. He didn't care which story you told yourself to sleep at night. What mattered were the predictions. And the prediction is clear. You will see local randomness, and you will later find non-local correlations when you compare notes classically. Any interpretation that gets you to that experimental result without contradicting relativity is, in a sense, valid. But the key point, the point he would hammer home, is that none of these interpretations block universe, many worlds, or even the standard collapse picture allow for usable faster-than-light communication. The no communication theorem stands as a mathematical fortress. It is the reason our textbooks don't have chapters on quantum email. The universe has built-in censorship. It allows for correlations that seem magical, but it forbids us from using that magic to talk. So, let's bring it all home. You have two particles entangled. You separate them. You measure one. What happens? Locally, for you get a random result. Your experience is indistinguishable from measuring any old particle. Globally, for the system, the description of the pair updates. The probability cloud condenses. For the distant particle, from its perspective, nothing. It's just a particle. When someone measures it, they will get a random result. Their experience is also local and normal for the correlation. A fact about the relationship between those two future or simultaneous measurement events is now determined. That fact was implicit in the initial entangled state. For communication, impossible. The distant experimenter sees only noise. The signal, if you can call it that, is hidden in the correlation of the noise, which requires a slow classical key to unlock. The spookiness is real, but it's a spookiness of interconnectedness, not of influence. It's the universe telling us that at its most fundamental level, separateness is an illusion. Things that interact once remain part of a single describable whole, even when they are light years apart. But that whole doesn't grant us the power to shout across the galaxy. It just sits there, a silent witness to the fact that reality is stranger, more subtle, and more beautifully constrained than our science fiction dreams. So why is entanglement not communication? Let's find the answer to that with the brutal, elegant clarity Feynman demanded. It's not communication because communication requires a controllable signal that encodes a message, and entanglement provides an uncontrollable revelation of a pre-existing correlation. Think of it like this. Imagine the universe, at the moment it creates an entangled pair, prints out a single cosmic lottery ticket. It then tears that ticket in half. One half says in invisible ink, if measured on axis A, you will get result X. The other half says, if measured on axis A, you will get the opposite result. They are a matched set. I get one half, you get the opposite. We fly apart. I choose to measure on axis A. My invisible ink becomes visible. I see up. At that exact same instant, not because of my look, but because of the initial tear, the invisible ink on your half, light years away, also resolves. It now reads down. But you haven't looked yet. Your ticket is just sitting there, its message now definite but unseen. Did I send the word down to your ticket? No. I performed a local action that revealed the truth that was always locked into the structure of our shared ticket from the beginning. The correlation was encoded in the tear, not in my look. Your ticket's truth was always the mirror of mine. My measurements simply illuminated both sides of the mirror at once from my perspective. For you to know that truth, you must perform your own local action. You must look at your ticket. And when you do, you'll just see a result. You won't know if it's the mirror of mine or just random noise. To know it's the mirror, you need the classical slow message from me with my result. This is the big reveal. The spooky action is not a signal. It's a synchronized revelation. The universe has a way of making sure certain distributed facts are consistent, and it enforces that consistency instantly outside of time as we feel it, because the consistency was never in time to begin with. It was in the initial conditions. Our measurements are just uncovering different parts of a single, non-local fact. We aren't talking to each other. We're reading from the same book, written in a language where every word is split across 2 pages. I read my page, and the word on your page is instantly determined, but you still have to turn to it to see what it is. This changes everything. It means the most profound lesson of quantum mechanics isn't about gaining new powers. It's about humility. It's about realizing the universe does not owe us a reality of separate push and pull objects. It offers us a reality of deep, mysterious connections, correlations woven into the fabric of existence that persist over any distance, yet forever hide themselves from our attempts to use them for control. Entanglement isn't a tool. It's a truth about the holistic nature of reality. And the moment we stop trying to see it as a cosmic telephone and start seeing it as a cosmic signature, a signature of a universe that is, at its heart, inseparable, is the moment we begin to think beyond physics as we know it. That's the beauty of physics. Not comfort, not simplicity. Truth. And truth is always stranger than you think. It takes our deepest desires for connection, for instant communication, for mastery over the cosmos, and shows us a reality that is more connected yet less controllable than we ever imagined. Entanglement whispers that we are part of a whole far greater than the sum of its seemingly separate parts. Now I want to hear from you. What part of this broke your brain the most? Was it the ironclad logic of the no communication theorem? The realization that from your local lab everything just looks normal? Or the sheer weirdness that the universe enforces correlations without sending signals? Drop a comment and let me know what you're still wrapping your head around. I read every single one. And if this video made you see the quantum world not as magic, but as a deeper, more constrained, and more fascinating kind of truth, share it with someone who still thinks we'll have faster-than-light quantum phones one day. Let's blow some minds together. Next time we're tackling the double-slit experiment, and trust me, if you think understanding entanglement was a trip, wait until you see what a single electron does when it's not being watched. It doesn't just confuse us, it actively, provably messes with the concepts of before and after. That's the beauty of physics. Truth. And truth is always stranger than you think.